This is recording, no? Somebody press recording? Or I press recording? I'm crazy. It's recording.
Yeah, it's already recording.
Okay, super. Now, let me share the webboard. The topic we are discussing now is called rational function. We studied in the first polynomial function. Now rational. Okay. Are you ready to pay attention? Ready, everyone? This is a little bit more complicated, right? Okay. What is the rational function definition? Definition first. And it's easy to understand definition because rational function is the division to polynomial. It's a rational function. Let me want to call f of x, maybe. A division to polynomial. So we have fraction. We have in the top p of x, in the bottom q of x. This is the classic way that so far we call this. F of x is a function. In the top we have p, and in the bottom we have q, and both p and q are polynomial function. And not necessarily the same degree, different degree, totally crazy. We're discussing any possibility here. Okay, in plural, functions. This is the definition. So let me analyze elementary, no too hard now. 1, 2, 3, 4 typical example in which I want to discuss in detail the idea behind rational function. But the rational function, you know, is different to polynomial because in the polynomial function, the domain is always all real number. It's nice, continuous, smooth, domain of real number, no restriction, never. But in rational, maybe yes, because the division, no? And when the division, you need to know that the denominator part never is zero. Si es zero, is undefined. Entonces, no, domain not always is all real number. Sometimes yes, but sometimes no. Okay, let's see example. Example 1. I bring typical example. You see new situation. Suppose que the function is f of x equal 1 over x. Wow, this is rational function, yes. Actually, this is the reciprocal function, but we can interpret que p es el polinomio, que es just 1, degree 0, and q is another polynomial, degree 1. Remember, degree is the exponent, no? Of the here. So 1, 1, 1, I can interpret it like a 0, x to the 0, no? Tan x is just x to the 1. That is the reason que es degree 0 and degree 1. Cool? Now, this is given in that way. Immediately you start doing the analysis of the rational function, the first thing that you should do is express it in factory form. And in this case, there are nothing to do because 1 and 1 and x is x. But in the majority of the example, it's super important. Don't forget this step. Express it, the rational function in factorial form. What means factorial form? Okay, you are doing the factorization of both polynomials. Polynomial at the top, polynomial at the bottom. Okay? And also inside the same example, the example 1, I need to investigate domain. Well, domain is easy. Domain is all real number except 0. Because you take the denominator part, you know that the restriction is not 0. Entonces now domain is all real number except 0. This idea is present in set builder notation is x such that x not 0 is equivalent in interval notation from negative infinity, comma 0, parenthesis, union, 0, comma infinity. Two different ways to express the same idea. Set builder notation, interval notation. And graphically, to understand this is, suppose that this is my number line. This is infinity positive, this is infinity negative. Actually, we have n0 a whole. We have a whole here because 0 is illegal. The rest is okay. Okay, this part is this part, this part is this part, and 0 as a whole. Because when you evaluate here, 1 over 0, you know, very, very well is undefined. So far, it's clear?
Yes.
Now we have more. Well. An x equals 0 is undefined, I know very well, but you have two kinds of to be undefined. We have the famous horizontal asymptote. I want to explain in detail horizontal asymptote, and it's a two kinds of to be undefined. Another is a horse. This is the classic undefined. And you need to determine in any problem si es asymptote or not, and si es a whole or not. In this case, it's asymptote. It's asymptote because you are doing the graphic of this. Let me show you. Not important now, not too important now. But let me try. The graph of this is the y-axis now. I introduce two dimensions. The graph of the function 1 over x look like that. Contain two branches, and this branch approach it, but never touch, never touch. Let me use another color, maybe green. Oh no green, black. The always is using black color dotted line to represent this thing I try to do is a vertical asymptote. Okay. Actually, the interpretation of this is my function when you approach it to 0, because 0 is the bad guy, you know. My y value approach it is going up, block up to infinity positive or infinity negative. This is the y value go to the infinity and y-axis, and here approach it to negative. And it's a classical vertical asymptote. There's no hole. Hole is another thing. Hole is the interpretation in the one dimension. But no. No one dimension. Two dimension. Okay, no hole. Okay. This is the first example. Maybe there are some things it's not clear, but little by little we approach it to the truth. And this idea for the rational. Example 2. On example 2, let me call different name. The name is the function of the example 2 is g. And we have 5x squared divided by x squared minus 5x plus 6. Okay, this is given in the problem at the beginning. And you see it's the division to polynomial. Actually, the polynomial in the top is not polynomial, it's monomial. Pero okay, es monomial of the degree 2. Degree 2. So there are no rules, guys, completely randomly. It's given at the beginning two polynomials. and you need to analyze the behavior in every case. And at the bottom, we have trinomial, 1, 2, 3. And again, degree 2. Okay, same degree. Let's see what happened. No, now. I promise, in your moment, I explain in detail what's going on when the degree is the same. Okay? Okay, now I need to express it, the rational function in factorial form. This is extremely important. Step number 1 is expressing in factorial form. You know very well, using synthetic division, factorization, either way, the way you prefer, or both together, depending on the complexity of the problem, do factorization the polynomial on the top and factorization the polynomial at the bottom. But in this case, there are nothing to do in the top because it's monomial. And the top, yes, is x, and the factorization is 3 and 2, both negative. It's a factory. Entonces, in this case, the domain of this function g is all real number except, okay, you take, remember, the part in the bottom, no 0, and no 0. And this is equivalent to say x no 3 and x no 2. Domain is all real number except this bad guy, que es 3 and 2. One possibility, no, to write this is using set builder notation is x such that x no 3 and no 2. In conclusion, si I visualize this in the all real number line, infinity positive, infinity negative, actually we have two holes. No, two holes, yes, and the one dimension picture. 1, 2, and 3. So we have a hole here, another hole here, and the domain is the rest from negative infinity to 2, don't touch 2, and between 2 and 3, don't touch 3, and from 3 to positive 3. Okay, so you write, if you want to write, because frequently happen in the test, express the domain in interval notation. Okay, it's from negative infinity, comma 2 parentheses, no bracket, because in 2 we have undefined, union 2, 3, union 3, infinity. Okay, this idea is equivalent 100% to this idea. Sometimes better expressed in that way, sometimes no, sometimes it's better expressed in that way. Either way, it's equivalent. Now, in that points, we have two vertical asymptotes. See, I analyze this in 2 dimensions. I included the y-axis here. Okay, so we have 2 asymptotes. Look at that. The convention to do, let me copy this part here. Negative infinity, 2, union 2, 3, union 3, 3. Let me erase that part. See more clear the idea that I want to explain now. So as I want to analyze the problem in 2D, I include the y-axis. We have into one vertical asymptote number 1, corresponding with this restriction. In 3, we have another vertical asymptote number 1, number 2, it corresponds with the second restriction. Entonces, it's important, I want to explain now how you investigate the behavior of the graph. Okay, maybe it's like that, I don't know, like that, and like that. They are different configuration. I am not sure 100% if this is good. Okay, one fantastic way you put in decimal, no? And you see, however, I want to explain analytically in the mathematical and the piece of paper how you can do that. Okay? Everyone follow me so far?
Yes.
Example 3 now. In the example 3, we have this. The name of the function is h of x is equal x plus 3 divided by x squared plus 4. Okay, we have again division to polynomial. The polynomial in the top degree is 1 because the exponent here is invisible 1, you know. And the polynomial at the bottom is 2 degree 2. And as I promised, in one moment I explain the consequence to have different degree. But it's okay. Degree. Okay, now if you want to investigate, no. You want to express the factory form. You are doing the factorization polynomial in the top and polynomial in the bottom. Polynomial in the top is just binomial. We cannot do anything. And polynomial in the bottom, it's a sum of the square. Okay, you know very well. Okay, this is impossible factorization. This expression is prime. Okay, to understand much better, okay, this expression is prime. Suppose that you don't remember, or I don't know, I never hear before the idea for the prime on in sum of a square. In different, yes, but in some, no. It's prime. You taking the polynomial in the bottom and you enforce it to be zero. Okay, I know it's illegal, no? It's to be undefined. So you try to solve this quadratic equation. So temporarily, to understand much better, you replace this symbol for equal because I am more countable solving equation, no inequality. But let's say you move the 4 to the other side, like a negative 4, apply a square root, similar to the thing we are doing, of apply application square root principle. Okay, so we have x. And here we have complex, or actually no complex, imaginary, pure imaginary. So square root negative 4 is 2i. And don't forget double solution because remember the complex is coming by couple of coin. Okay, so now the supposition in this topic, in this chapter, we are working not in the complex field, we are working in the real field. The supposition of the domain is always all real number except restrictions. And the restriction you investigate and you discover, wow, the restriction living in the complex field is completely outside the all real number. Therefore, when this situation happens, the meaning of this is okay, the domain is all real number. The domain of the function h of x is all real number because we have no restriction in the real field. The restriction is in the complex, and the complex belongs to another planet, another field, another thing. Is not important for me. Clear? This is not frequently, but sometimes happen. Okay, you investigate, and you enforce something in algebra. In algebra, you want to find the intersection, for example, between this curve and this curve. And you have the equation of this and the equation of this. Equation 1 and equation 2. And you enforce it to be equal because I want to find the common point. And when you solve this, you get complex. And the interpretation of this is, this curve never touch. Okay? It's a classical in algebra. Okay, so we have no asymptote. Very good asymptote. known in this problem. So when you are doing the graph of this, I don't know, maybe look like that. So we have no, this is the x-axis, no asymptote. I suppose, I don't know exactly, but I try. It is something like that. Oh, no asymptote. It's totally different. Formula. This is roughly sketch, no accuracy. After I promise we are doing accuracy. The last example, to illustrate any possibility. Example 4. Do you follow me? Example 3 was clear or no?
Yes, it was clear.
Okay, cool. Example 4 is super interesting. Pay attention. Suppose the function rational p get the division to polynomial. The first one is x squared minus 11x plus 30. And the bottom we have x squared minus 9x plus 18. Okay, again we have polynomial degree 2. And we have here polynomial degree 2. Okay, same degree, something good happen when it's the same degree. I don't know now, but I anticipate it, yes. Okay, but the thing you know very well is the factor 4. Sometimes this process too long, sometimes no. Depende, no? The polynomial. Depende the polynomial. But you know very well the technique we explain of the factorization. Factorization, or when it's impossible factorization, well, you are doing by a scientific division. And you help me with the Descartes rule, the rational zero polynomial, and of course our good friend Desmos can help me to understand this. In this case, super easy. I don't want to complicate that part now. And your factorization, the polynomial on the top, your factorization, the polynomial on the bottom. This is xx, this is xx, and the combination is 6 and 5, no? Because 6 times 5 is 30, and 6 plus 5 is 11. Both negative. Good. And at the bottom, the combination is 6 and 3. Because 6 times 3 is 18, and 6 plus 3 is 9. And again, it's minus. Wow, you see, one important thing happened now. Pay attention, this is a crucial moment. You cancel out this and this is the same. And you know very well, when you have any expression divided by itself, and well, that is a fructification, or this is the reason I cancel, I obtain one new expression that is x minus 5 divided by x minus 2. Okay. Interpretation. This is most important moment now. Interpretation. Okay. Actually, what is the domain of the function p? The domain of the function p is all real numbers such that, and the bad guy in this game is you take the polynomial in the bottom, but no include this, the guy that we simplify. I want to explain in detail that part. So basically, it's no 6 and no 3. Okay? See, I want to visualize graphically. You get the famous all real number x. It's infinity positive, sorry. Oh, okay, x is the axis. Infinity positive, infinity negative. And we have two bad guys. We have 0 here, we have 3, 1, 2, 3, 4, 5, and 6. Okay. We have here undefined, and we have here undefined. Therefore, if you want to express this idea in interval notation, is from negative infinity, comma 3, no include 3, union 3, comma 6, union 6, comma infinity. However, if you analyze this in 2 dimensions and you put the y-axis here, okay, the type to be undefined is different in 3 and 6 because 3 stay after the simplification. Therefore, in 3 we have vertical asymptote, exactly the same we see before. But in 6, no. Okay, entonces, what is the shortcut? What is the conclusion, professor? The conclusion is at x equals 3, we have vertical asymptote. However, at x equals 6, que es the factor que is cancelled out, we have a whole. So there are 2 kinds to be undefined of vertical asymptote or whole. Suppose que I put in decimals, they see the graph like that. This is the classical behavior in the vertical asymptote. Not exactly always like that, but in this case, it's like that. However, how you represent the whole? Well, the whole you represent here, okay, by the way, when you put in decimal, you don't see the whole because the whole is infinitesimal. Actually, we have a whole here. Okay, after I want to explain how we can see in decimals. So my curve is this branch, this branch, nice. This is asymptotically, guys, by the way, asymptotically, I want to show you after, is something like that. The curve, this is the asymptote. And the curve approach but never touch. Never touch and never cross. So the distance is small, but never touch. Of course, never cross. This is illegal. No cross. This is in the vertical. We are talking about vertical. We have different asymptotes. We have vertical, horizontal, and slant. And we study everything, right? Now, in this case, is asymptotically again, approach but never touch. Here we have a hole. The hole is invisible because you know it's 1 point. So 1 point have no dimension, and you don't see. You believe que it's continuous, but actually it's not continuous. And I want to prove in decimal how you can see this. Okay, but the most important is not the picture. No, it's the concept behind this. Okay, the first thing that you should do in the analysis of the rational function is your factorization. Factorization the polynomial at the top, factorization the polynomial at the bottom. If by coincidence some factor is repeated, you delete, and the factor gets repeated as a whole. The factor can stay in the bottom is a very cost. End the story. Another way, some classical question que the student asked me, bueno, professor, I don't understand something. This is the original, just giving and the problem at the beginning. And this is the rational function is given at the beginning, and the name is P. I call P. And this is equivalent 100% to this? Or no? The answer is no. The answer is no. P actually, we can call another name, no P. I don't know, what, another name. However, the true thing is that this is equivalent 100% under this restriction. This, when you include and exclude the 6, yes, This is 100% equivalent to this. So now you don't need to know and detail this idea. You working in the majority of the scenarios. You working with this. This is equivalent. I suppose it's 99.9999% to the region. The region is ugly. It's complicated. This is easy. You working with this. But keep in mind, in 6 no, because in 6 we have a hole. Therefore, the graph of this and the graph of this are equivalent, except the hole. Because you are doing the graph of the original, we have a hole, I did here in blue color. However, if you are doing the graph of this, the green, you see something like that. It's the same graph, but here we have no hole. It's the same graph point by point except in the hole. You here exclude the hole. This idea is super clear or super confused?
Professor, can you explain horizontal asymptotes?
In your moment, yes. I promise.
Thank you.
My question was, the thing I explained so far is clear for you?
Yes.
I talk too much. I promise. Can we explain in detail now? Right now, vertical asymptote in detail. How you find and what are the possibility that we need to analyze. But of course, after when I finish, we study horizontal. Asymptote. Vertical asymptote. And horizontal asymptote. And why not slant asymptote? Pero slow down. Be patient. Total. Okay? This is pending. Today. I suppose que today. Yes. Okay, any other question? No problema. You understand the basic idea? You understand what is the definition of the rational function? Number one, a rational function is a little bit different to the polynomial. Yeah, Jenny. Jenny, entonces es more complicated, ¿no? Because you introduce a new concept, new idea. Okay, let me explain in detail now the vertical asymptote. Of course, I put 2 examples to understand, my opinion, good. Vertical asymptote. So, what is the definition that? Definition is definition is what happened with my pen? Definition is the one point when the x approaches to this point. I want to call C. This is the value, it's 2, 3. Example we see the function, semicolon, the function approaches to infinity positive or infinity negative. Okay? And we have different scenarios. Let me try 4 scenarios for different situations. Suppose the famous point C, and we have here vertical asymptote. We have the famous point C, we have vertical asymptote. We have the famous point C, and we have vertical asymptote. We have the point C, and we have vertical asymptote. And this is my famous x-axis, y-axis. For example, you have that situation. Ooh, in this case, happen infinity, positive or negative. Look, but in calculus, when you take calculus, you study new tools to analyze this idea, but it's easy. So when the x approaches to c, maybe we have two possibilities: approach to the left or approach to the right. X approaches to c to the right. In this scenario, the function f approaches to infinity positive. Look at that, because the y value is going up infinity positive. However, in this scenario, to the right, with respect what? The point C, right? Suppose que C is 2. Suppose to see more clear. Okay, suppose maybe definition using letter, but in the example, no. Suppose que this is 2. To left, to right. What means to left, to right? To left is before 2, maybe 1. Or, okay, the basic idea is a little bit close to 2, but not necessarily 2. 1.9. Okay, the function, que the y value approaches to infinity. It's going up. And when you moving approach to the 2, but to the right, like a 2.1, 2.2, so the function is going to the negative infinity. I said this is super easy to investigate. This is no big deal. If you take the function, you know that the function in 2 is undefined. You evaluate the function in 1. Suppose que the function 1 is positive number. And the function in 3 is also positive. Es negative, sorry. Entonces the behavior look like that. Ajá, entonces, ¿es eso the only one possibility? No. We have possibility look like that. When you approach it to this example is 2. When you approach it to the left. The function f of x approach it to positive infinity. And when you approach x to the right, approach. There are many examples to see that. It's positive infinity both. Positive infinity both. Go up, positive infinity. Oh, like that. This is negative infinity, and this is positive infinity. It's completely opposite to this. Oh, like that. Negative infinity, and negative infinity is completely different. But don't be scared, because it's too easy. You evaluate the function. Plugging in. One value before the asymptote and one value after. And see it's positive. And this is positive. Not necessarily equal. We select not symmetrically. So it's this kind of behavior. And here is negative. And this is positive. It's this kind of behavior. And these both are negative. It's this kind of behavior. Cool? No secret. Super clear. Okay, so now let's move on to I bring 2 examples to illustrate very well this idea. Example 1. Example 1 always is easy. I kindergarten example. Let's use it. Suppose the function is given is f of x is equal to over x minus 1. Oh, easy. This is degree 0. Polynomial degree 0. And this is polynomial degree 1. So this is not important now. This is not important. So now, well, I realize it is, so you take the polynomial in the denominator, que es q, remember. Let me so far try to systematic the procedure to find the asymptote. You take the polynomial. Remember, Definition was P of x divided by Q of x. And you take Q, it's the bottom, and enforce it to be 0. Oh, those are x equal 3. We have, of course, the vertical asymptote. Okay, so see, I want to do the graph by hand. After you see them, please. By hand. Suppose, let me try to use. Oh, no, okay. I can using maybe a rectangular coordinate system that I have here in my computer. Okay, here, over there. Okay, there you go. I bring this guy. Okay, so now I want to do roughly sketch. After I explain super detail. So far it's roughly because we are beginner now. So I discovered that at x equal 3 we have vertical asymptote. Cool. So vertical asymptote, you using the rule. Okay, 90 degree because it's vertical. 90 degree, and 3. Say 1, 2, 3. Okay, so I do that. Of course, the convention for the vertical asymptote is always dotted line, black color. And you see how we are doing this with this idea. Okay, cool. This is our vertical asymptote. We have only one. And to understand what is the behavior, I propose you evaluate f, evaluate at the 1 point before and 1 point after, maybe 2 and 4, no? Why not? Evaluating 4. You evaluate 4 is 2 over 4 minus 3. 4 minus 3 is 1, and 2 divided by 1 is 2, and the famous point is 4, 2. I plot this point. I'm using the red color, no? 4, 2. 4, 2. Wow. This is my first point. And evaluate at 2. Because remember, the asymptote is located in 3. So evaluate 2, entonces 2 over 2 minus 3, and 2 minus 3 is negative 1, entonces es negative 2. And the famous point is the point 2, negative 2. 2, negative 2, 2, negative 2, 2, negative 2 is 2, negative is here. Okay, I don't know the rest, but using my imagination so far, I promise after we study more detail, our graph look like that. Wow, no good. No good. Let me try my best. It's complicated by hand. Remember, the most important is this is wrong because the curve approach it will never touch, but the distance is smaller. Okay? It's asymptotically approach. Cool. So in this case, only one vertical asymptote. This is the behavior, and no hole, no nothing, right? Okay, now let's move into Desmos to visualize more elegant. Desmos. Let me share the screen. Cool. Desmos. You see? You see?
Yes.
Look at example 1. Is the function 2 over x minus 3 exactly I put in the paper. Bang. Okay. Look, it's fantastic because you put the function. You using function notation. Remember, you can use in this mode if you want. You put y here. Y equal 2 over x minus 3. Desmos understand very well because Desmos understand very well the y and f of x is the same. Okay. However, what is the advantage of the f of x? Is that you can prove it indirectly without a decimal compute for us the value, que es 2 or negative 2. And you format the point like a 2, f and 2 and 4, f and 4. Okay? I plot the point and the asymptote, look at that. The asymptote is this. The asymptote is the classical vertical line, x equal 3, you put here, and you change the color always black, and you change the style always dollar line. Okay, this is a convention that we are using in any graph in this subject. Asymptote, black color, dotted line. Okay, and now in the test, if you want, make a screenshot or download the picture here, you know very well how. It's here. No, it's here. Hold on, it is here. Here, it's here. Export, yeah. There you go. Convert to the image, and that's it. Oh, a screenshot. A screenshot are using a snipping tool. I don't know if you see or not the snipping tool. I get the image in the screen of our computer. So far clear, guys?
Yes.
So we come back to the whiteboard. Let me try. One more. Whiteboard. Do you see whiteboard?
Yes.
Let's move on to example 2. Let me erase that part. And why not that part? Because I use it. No. Example 2 is a little bit more interesting. Is the function g is equal x minus 3 divided by x squared minus 5x plus 6. Okay, entonces the degree of the polynomial on the top is 1, linear. The degree of the polynomial on the bottom is 2, quadratic. Okay. The factor 4 is, well, in the top we cannot do anything because it's too easy binomial, but in the bottom, yes, it's trinomial. This is the classical factorization. 3 and 2, negative. Wow, and you see clear like water. Okay, this is cancelled, and stay alive. 1 over x minus 2. So in conclusion, I realize that at x equal 3, we have a whole. You see how you graph in the whole. At x equal 2 is the expression can stay in the denominator. You enforce it to be equal 0, and get q x equal 2 is we have very fast. Cool. Okay, because this graphic have only one very fast at 2. Okay. So I make a zoom to see more clear. At x equal 2 gets here. We have a very fast. Because I don't know very well the behavior. Maybe is when you approach it to the left or to the right, is infinity or no. And you select, why not, in the asymptote into two arbitrary points to the left and to the right. Obviously, in 3 no, because in 3 we have a hole. So my function g evaluated in 3 is undefined. Likewise, the function g evaluated in 2 is also undefined. There are two different reasons to be undefined. This is a hole, and this is the vertical axis. The vertical axis is easy to see. Actually, I did that. Vertical axis. Okay, so in order to see the behavior, you evaluate the function g, maybe in 1, it may be in 4. Arbitrary value, you select before the asymptote. In 1, let me try. You can use the original. Of course we can. But we can use in this case easier. Of course we can, because they are equivalent 99.999%. The only bad guy, so the only thing is different is in 3. So this is not 3, because in 3 I know that we have a hole. But the rest is equivalent. So you only want 2 very easy to plug it in here. A 1 over 1 minus 2. A 1 over negative 1 is negative 1. And the point is 1 comma negative 1. 1 comma negative 1 is here. 1 negative 1. Boom. That point. Yes. Now another point was 4, maybe, no? 4. 3, no, because 3 is a whole, right? Okay, this is then I get 4 is 1 over 4 minus 2. Using again this. We can use it always this except in 3 and in 2, of course. So it's 1/2. Because 4 minus 2 is 2. And the famous point is the point 4 comma 1/2. Let me try to do my best. 4 comma 1/2 is here. This is 4. And 1/2 is the half of this over there. 4 comma 1/2 positive. Oh, I'm crazy. Guess this. 4 comma 1/2 positive. This is 1. This is 1/2. Okay, now using another technique I want to explain after. Now I believe I realize a little bit my graph look like that and like that. One of professor, but I don't understand something. I don't understand. You see, in 3 we have a hole. Oh yes, yes we have a hole, and the hole is, I suppose, is here. I don't know exactly at what point, but I can investigate. The hole is, you know, is, the hole is open circle, no, like that. Now, I don't know exactly where, but I can find, because remember, this expression and this expression are 99% equivalent except in 2 and in 3. But see, I take this, you evaluate n3, you evaluate this. Let me call this function is no, so the name, let me put the name, this is g. G is the original. This is G prime. Let me go, or G1, no prime. Prime is another thing in mathematics. G1. Or any name, guy, Maria, Jose, doesn't matter, the name is not important. So G original is equal G1 in X and no in 3. I want to evaluate in 3. So what happens when you evaluate G1 and 3? G1 and 3 is 1 over 3 minus 2. And 3 minus 2 is 1, and 1 over 1 is 1, and the point is 3, 1. So this is useful to understand the position of the hole. The position, okay, look like a little bit similar to the thing I did before. It's in 3, 3, this is 3, 3, 3, what? 3, 1. No, not good. My graph is not good. Let me erase that graph. 3,1 is here, 3,1. And the graph look like that. Whole, this is not whole, this is actual value that I plug in your moment for. It was 1/2. Point was 4,1 half. This point was 1, -1. And this do not exist. But the location is in 3,1. How do you know? Because I am using artificially no G. The G, the graph of G is the graph that I put in red color. See, I want to do the graph of the G prime, G1 in blue color of X. It's coincidence 100% or 99.9 except the whole. Okay, the whole G1 have no hole. G1 have no. Do you understand this idea or no? What's confusing?
I understand.
Excellent. This is classical, guys, in calculus. In calculus, you need to know that is the reason that this is pre-calculus. Es, bueno, this is the integrated algebra, pero integrated algebra is called algebra plus pre-calculus. And we have more pre-calculus than called algebra. Okay, cool. This is the idea behind vertical asymptote. And why not the idea behind the holes. Let's move on now to the horizontal asymptote. I can erase the board. I can? Yes. Now let's move on to now horizontal asymptote. Entonces, don't worry too much because now today is the theoretical part. I promise okay, in one moment I will bring example, and this example cover everything. Cover asymptote, horizontal, vertical, blah, 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 blah. And another thing that is useful to make a graph of the rational function. Horizontal asymptote. Definition, what is that? Well, this is easy to understand. Because you understand in the polynomial function, the end behavior is similar. It's the end behavior. Entonces, es end behavior. What means end behavior? Let me reinforce it again. It's when the x approaches to positive infinity or negative infinity in both directions, to the right and to the left, suddenly happens that the function approaches to one value. Okay, I want to call D. Amazing. So now, all will happen que in both directions, positive infinity and negative infinity, is the same value. This is valid, this idea is valid only for the rational function. There are another function, not rational, using radical maybe, or exponential that we studied in your moment. Okay, no. So now, and this is completely symmetric. Look, let me show you different scenario of the typical horizontal. Horizontal is, I want to investigate the end behavior of the function. What means end behavior? End behavior means what is the y value, what is the function value when the x approaches to infinity positive, infinity negative, no? In both directions. This is the x-axis, this is the y-axis, this is the x-axis, this is the y-axis. And we have different possibilities. One possibility is, suppose the horizontal asymptote, of course, corresponded with the horizontal line. And the horizontal line is a line that contains slope 0. Okay, suppose this example, suppose. Bam, 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 bam. Bam, 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 bam. Bam, bam, bam. Do you see the difference between vertical? Vertical is like that. Bam, 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 bam. And the horizontal is horizontal. And suppose the function, suppose, hypothetically, the function look like that. I put an arrow to indicate that the function continues forever to the right and to the left. Positive, positive, infinity, negative, negative, infinity. And the beauty is that both values is the same. Another function, no. Another function, the behavior in infinity is different to negative infinity. But in rational, no. I guarantee 100% it's the same. Well, we have another possibility, que is a combination that we have in my problem, horizontal and vertical. Mostly we have one vertical here. Bam, 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 bam. So it's something like that. Okay, this arrow indicate us the approach, but no touch, don't touch. And like what? This continue forever, infinity, and this is continue forever, and one value okay, I call D. This value D is this value, look, D. Y equal D, D. This is the value. And sometimes can never happen in the vertical. Our curve crosses the asymptote, and after put asymptotically, and never touch. But at least one point. And this point is super important. Determine in your moment, I want to explain how we determine this point. This is an important point that you always need to check it. Sometimes, in this case, no, do not exist. Do not exist the famous point in which the curve in red color touch the asymptote or cross it. This case, no, 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 no. However, this, yes, exists. Okay, and it's an important point. I need to investigate X and Y. Bueno, Y is D, the value for them. Okay, entonces, what is the analysis that you should do to investigate the horizontal? Okay, let's see example. The example you see clear. This is example one, of course, example one of the horizontal. No? The example one, we have a function f of x equal 7x squared plus 2x over 4x squared minus 3. Okay, the first thing you should do, guys, always is the analysis of the degree. Now this is important. For the horizontal, it's super important. The degree of the polynomial in the top and the degree of the polynomial in the bottom. And when you have the same degree, yes, we have what? We have horizontal asymptote. This is the clue to give me information. See, when there's the same degree, yes, we have. But where? It's another challenge. Where? What is the formula? What is the equation for the horizontal? Y equals D. But who is D? Who is D? Well, okay. You analyze in each polynomial. Look, in this polynomial, you analyze what is the dominant. What means dominant? Is the term increasing faster. It's obvious that depends on the degree. So basically, you need to understand the 7x squared plus 2x, this guy increasing when the x approaches to infinity, no? To understand, to model approach to infinity, you plug it in, for example, in x, 1 million, 2 million, 1 billion, 3 billion. It's a huge number, right? But this increasing faster. Do you see increasing factor? Because it's a square. So the higher exponent gets the degree, by the way, is the dominant. So the dominant in the top es obvio que es 7x squared. And the dominant in the bottom is 4x squared. Now you completely delete, ignore, negligible this guy, bam, bam, and this guy. Do you understand this or not?
Yes.
Aha. And now, see, the degree is the same. We can simplification again. This 7 over 4. And this is our D. So basically, I discover que yes, we have horizontal asymptote at the line y equals 7 over 4. Boom. Finalize. Well, for a moment, finalize. Clear? I bring 2 examples, and you help me to analyze in these 2 examples what is the, well, first of all, question 1, if you have or no horizontal. Yes, no, yes, no, yes, no. Secondly, our value. In the case, yes, exists, we have our value. Example 2 and example 3. Example 2 is easy. It's h of x is equal 8x squared plus 9x minus 5 divided by 2x squared plus 1. Okay. And the second is p function is x squared plus 7 and 11 minus x squared. And example 2, what do you think? We have yes or no?
Yes.
Yes. Why?
Because they have the same degree.
Super. This is the reason. Degree of the polynomial on the top. I call this guy analysis of degree. Same degree. The answer is yes. Yes, we have. We have horizontal asymptote in this function. At what value? In the second question.
At y equals 4.
At y equals 4. And where come from this 4?
You divide 8x squared over 2x squared.
Exactly. You divide 8 divided by 2, not necessarily x squared, miss. Either way, the way is correct. You're doing well. 8 divided by 2 gets the leading coefficient in the polynomial on the top and the polynomial in the bottom. Super. This is the answer. What do you think about the second? Okay, I put a little bit confusing, no? Because I want you make a mistake. A warning, something weird, right? My question is again, we have horizontal yes or no, at what value?
Yeah.
I don't hear.
Yes, at y equals -1.
Super cool. Super cool. She said, yes again. Degree 2. Degree 2. And I, to confuse you, I put in weird way. But you take coefficients leading in from this and from this. And 1 divided by -1, yes, at the line y equal -1. End the story. Cool. Very well. It look like easy, eh? Or no?
Yes.
Yes. The problem is that we have different options. So we, unfortunately, we have another case in which you have horizontal asymptote, okay, called special. Special is, let me show you. A special case. A special case que we have horizontal, but not necessarily it's the same degree. Okay, suppose this example. Example, what is the number? Example 4. Example 4. Suppose the function that I want to call h. This is 5 over 4x squared plus 9. Okay, we have a rational function. Okay, and my goal is analyze the horizontal, because I am doing the analysis of the degree. The degree of the polynomial on the top is 0, and the degree of the polynomial on the bottom is 2. And when the situation happens, when the degree of the polynomial on the bottom is greater than, no, greater than 1, greater than 2, greater than, in general, 2 is greater than 0. No? Yes, we have, but we have a special case of horizontal asymptote. Okay, always is at y equals 0. And make it sense or no? For you in your mind, make it sense. Okay, when you divide two polynomials, look, p of x divided by q of x. However, when the degree is the same, it's nice, because this polynomial increasing in the same speed of this. That is the reason at x equal infinity or negative, this stabilizes to the one value, okay, d. However, when the degree of the polynomial p over q, but this increasing faster than this, or this no, this stay constant, because in this example, phi is constant function. It's obvious that if you divide one thing that is smaller than this and is increasing, the y value go to 0. Do you see this or no? I want to explain. Si the denominator increasing faster, so si the number que plugging in the denominator is 1 million, 1 trillion, the division is smaller. Yes, smaller, but no negative. It's 0, right? It's clear or confusing?
It's clear.
It's clear, for sure. No necessarily one example to illustrate this idea, or no? Oh, yes.
Yeah, let's do an example.
Do you like, no? One example. Look. Suppose the reciprocal function is super elementary. Degree 0, constant, and this is degree 1. Linear. I'm plugging in different values to investigate the behavior. Suppose x equal 1. 1 over 1 is 1. Cool. X equal 10. My goal is increasing faster. This 1 over 10 is 0.1. Suppose x equal 100. Is 1 over 100 is 0.01 in decimal. Suppose 1000 is 1 over 1000 is 0.001. You see how this number is to be smaller, and never negative, it's positive. That is the reason that this is the interpretation of this. Cool?
Yes.
Excellent, beautiful. Now I bring one example to illustrate very well everything about horizontal asymptote and any complication analysis of the degree. Okay, we are doing something. First of all, I will give you one rational function. You investigate, see we have or no horizontal asymptote, and determine what is the value of that horizontal asymptote, and include the analysis of this if the curve crosses or not. It's the new thing I want to explain now in this example. Okay, let's do it. is example, I don't remember. Example 6, no? Maybe. I don't know. Example. Look, suppose the function is giving f of x is equal ax squared plus 9x minus 5 2x squared plus 1. And my goal is, number one, we have horizontal asymptote, yes or no?
Yes.
Yes. Because the degree is 2, es de clásica, no especial. And this degree is also 2. The answer for that question is yes. At the value y equals something, no? Y equal what?
4.
And with this similar problem. But the new thing that brings me this is I want to investigate if that function crossed this asymptote. Cross it. This is the second challenge. The function f cross it. The horizontal. It's easy. You remember when you want to investigate something, you put together, right? You want to find, see this curve cross it or no? This curve. You put the equation of this, equation 1, equation 2, you put equal each other. See the answer is one value, nice, it's 1 point. The answer is 2 value, nice, it's 2 points. See the answer is no solution because it's complex maybe or no, or you see contradiction in the equation. Entonces no. But at least I try, no? How you try? You take the original equation of the function is ax squared 9x minus 5 divided by 2x squared plus 1 equal. You enforce it to be 4. Okay. This is equal to this. Okay, no big deal for us. You apply maybe cross multiply like that. And of course, I suppose that this denominator is 1, no? Because 4 is a whole number, no? 4 is 4 over 1. You multiply ax squared plus 9x minus 5 times 1 stay the same. And 4 times this, 4 times x squared plus 1. Something like that. And you solve this equation que look like, I don't know if it's true or not, quadratic equation. I apply distributing ax squared plus 4. Oh no, it's not quadratic because I see that this guy and this guy cancel out. So we have linear equation. This linear equation, that means que touch or cross in only 1 point, not 2. Let me try to do my best. 9x is equal minus 4 minus plus, it minus is minus, right? Why minus? Plus 4 plus 5, and 9. But by 9 both sides. Oh, x equal 1. So I discovered, yes, exists the point at x equal 1. So you want to express it like order pairs, x comma y, for the x value is 1. I discovered the famous point in which that function crossing the horizontal asymptote is at 1 comma something. What is the y value associated with this one? In your opinion?
4.
Exactly, because it's the value of the asymptote is y equals. Cool. Very, very well. Let me show you in this most, because I consider it important or interesting at least, the graph of this function, and you see clear that situation. Let me try. This is no good. Yeah, it's the best. Okay, look at that. Let me share the screen for this Desmos. No. Yes. You see?
Yes.
Excellent. Okay, I prepare for you this as a function. I type in this. Boom. Look at that. Look at that. This is the graph. This graph, guys, I don't understand very well now. What is the reason that we have no vertical asymptote? But it's not important for me now, vertical asymptote. Important for me now is horizontal. The horizontal is at y equals 4, que es this. Look. And the famous point, the curve, que es in red color, touch the asymptote is at the point 1, 4. Let me take advantage, because this one picture is much better than 1,000. See what is the idea behind horizontal asymptote. Look. Let me make it zoom. You see how the curve approaches the distance between the curve and the asymptote is smaller and smaller, but never touch. Only touch in the famous point that we discovered that was 1, 4. And it's a lateral in both directions exactly the same. This situation can happen que the asymptote, the horizontal asymptote is universal in both directions, positive infinity and negative infinity, only happen in rational function. In another function, the exponential or radical functions, we have two different asymptotes. To the right, maybe it's positive 2, and to the left is negative 2. But no, in this case, positive 4 in both directions. Cool? Do you see the idea?
Yes.
Cool. Okay, so you understand very well this. I propose you study the last asymptote, and we are almost ready to do one decent graph of the rational function. I want to explain one line guide, step by step, 7 steps, 1, 2, 3, 4, 5, 6, 7 steps. If we are doing maybe 3 or 4 examples. But okay, now slang asymptote. Another asymptote we study. Look, let me show you slang. What is a slang? Slang is how you identification that we have a slang or not. Of course, let's explain using example. It's more clear. Not theoretical. Suppose the example to illustrate slang. Example is the function is f of x again is equal x squared plus 1 divided by x minus 1. Okay, again, we are doing the analysis of degree. So the analysis of degree you are doing always for the horizontal and slant. The same analysis. However, it's important to understand that if you have horizontal asymptote, you have no slant. And if you have a slant, you have no horizontal. They are mutually exclusive. Okay? Now, the degree of the polynomial in the top is 2. And the degree of the polynomial in the bottom is 1. And only when the degree of the numerator is bigger than 1, the degree of the denominator is when you have a slant. Otherwise, no. So we have, for example, degree 3 and degree 2. Yes, because the 3 minus 2 is 1. So when the degree of the numerator is greater than 1, the degree of the denominator, so we have a slant. And see, we have, for example, 3 and 1, no. And of course, you have 2 and 2, no, because they're horizontal. And so you have, for example, 2 and 3 is also horizontal. This and this is horizontal. This is regular case. This is a special case. This is nothing. And this is a slant. Make sense?
Yes.
Horizontal asymptote, regular. Horizontal asymptote, special. This is nothing. Cool? And interpretation, geometrical interpretation for slant. Well. This is the oblique line, like that. Bam, 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 bam. So remember, we studied vertical, it was like that, da, 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 da. We studied horizontal, da, 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 da. Now it's a slant. Okay, this line contains, you know, it's like mx plus b, it's equation of the regular line that we studied in elementary algebra. We have y and z, and we have a slope. The idea is how we determine this. But it's an inclination line, oblique line, when the slope and y and z. So what is the idea? What should I do? What should I do? What should I do? Well, I can do immediately you detect the yes. Degree analysis of the degree. Degree 2, degree 1, yes. We have a slant. Asymptote. Good. Now, how do you determine the slant? Okay, easy. You apply long division. You divide because the fraction we have is improper fraction. And when the degree of the numerator is bigger than the degree of the denominator, this is called improper fraction. You need to find the proper fraction. So you divide. You are doing long division or scientific division, the way you prefer. And this possible is perfectly legal doing scientific because the denominator is degree 1, que es linear. But okay, either way, the way you prefer. Because I copy the polynomial on the top gets x squared plus 0x, very important, complete. See, one guy is missing, you put 0 in order to keep the order, right? And divided by x minus 1. Basically, you copy our rational function in the long division format. And we are doing long division. It's obvious it's x because x times x is x squared and x times -1 is negative x. You see it's important when the one guy is missing and the polynomial you put 0 in order to keep the column que corresponde second power, first power, 0 power. By subtracting, you change the sign. It's cancelled. And this is just x and bring downward. I continue, of course, because the remainder we have this is degree 1 and this is degree 1. So we have to you stop the long division or scientific division when the degree of this is smaller than this. So degree 1, degree 0 is just a number. Suppose plus 1. 1 times x is x. 1 times 1 is -1. I subtract the change the sign. It's cancel out, and the answer is 2. Okay, so now, in this crucial moment, I rewrite the function f of x like this. You copy the quotient is x plus 1, plus, you copy the remainder, is 2, and you copy the divisor, is x minus 1. Okay, I guarantee you 100% that this expression is equivalent 100% to the original. But on the original, you don't see anything. I am totally lost. However, in this, I am more clear. That part is the slang asymptote. Okay, why? How do you know that? Because it's the classical y equal mx plus b. O sea, es, pues en general, mx plus b, b is 1, and m is 1. Oh, it's a coincidence. So now, if you want to do the plot of this, the rectangular coordinate system, let's do it quickly, but today is the day of the theoretical part, not too much detail. It's only understand every scenario that we have. I suppose the image of the, yeah, there you go. Wow. This is my rectangular coordinate system. Okay. Entonces I can see clear like water que in this equation que corresponde with the slant part, slant asymptote part. Uy. Es obvio que es a line. Y si es a line y es asymptote, es dotted line. Passing through, the y and z is 1. Look at that. I plot this point at B. And wrong and right, 1 up, 1 to the right. We get the second point, and we're connecting both points using the rule for 45 degrees. There you go. We're connecting that. Of course, it's an asymptote. Yes, an asymptote. We have dotted line in black color. Oh, black color, dotted line, asymptote. It's a convention we are using every day to do the graph of the asymptote. Wait a second, I did wrong. I want to take advantage. This is this graphic of this. This is the graph of the y equal x plus 1. This is now. Complementary of this, I can see that part is a vertical asymptote. Not necessary doing any long division, any scientific division, to realize that the expression at the bottom is you enforce x minus 1 equals 0, x equals 1. Therefore, I can find one vertical. This is the vertical. So no excludes. So exists in one problem vertical and slant. Vertical and horizontal. Never exists slant and horizontal. This is exclusive. But vertical and slant, of course. We have in one vertical. Oh, vertical is 90 degrees. 90 degrees in one. In one. Here. Another asymptote. Pero es vertical. Oh no. That color. That color. That color. Black color. Let me erase green color. Black color. Black color. Don't worry too much for this because we are doing lessons. Few seconds. Go. This is the vertical asymptote. Okay, no more rule. We have vertical asymptote and we have slant asymptote. On the graph, ID en Desmos, let's see que es something like that. I promise I explain detail how you determine different points. Yeah, no idea. But so far it's the idea that I want to explain. Okay, one more example of slang, theoretical. Do you understand the idea or no? This is example
Yes.
1 of slang and example 2 of the slang. Suppose G is the name of our function. A division 2x squared minus 5x minus 3 divided by x minus 2. So immediately you see that, you see, wow, what the hell is that? Well, es obvio que the degree of the polynomial in the top is 2. And degree of the polynomial in the bottom is 1. So what do you think? We have do we have slant asymptote? Yes or no? Question mark. This is my first question.
Yes.
Yes. Because the reason is because the degree of the top is greater than 1. Si es 3 and 1, no. The degree of the. Okay, cool. My next question is, what is the slant asymptote equation? Well, long division, or synthetic division, either way. What way you prefer, guys? Synthetic division or long division? Because in my paper, I am doing, but let's do it both ways. Let's do it both ways, both. Okay. Let me explain in detail this idea. Long division is universal. You can do always. Synthetic division is particular. Only when the degree of the divisor is 1. This case, fantastic. Yes or no? So there are no reason. To apply long division. I don't know. Si you lie, it's your problem. Suppose synthetic. For the format for the synthetic, I put 2, -5, and -3. And don't forget, this is the only detail that you don't forget. You put 2 positive when the factor is negative. Because in synthetic, you change the sign one time. In long division, no. In long division, you're subtracting, change the sign. Subtracting, change the sign. Subtracting, change the sign. And in synthetic, no. Change the sign one time, and that's it. And you bring down to multiplication. 2 times 2 is 4. And -5 and 4 is -1. And this and this is -2. And this is -5. I don't care too much that part because this is the remainder. Important for me is the quotient. Okay? The quotient is x to the 0 and x to the 1. Therefore, the slant asymptote equation is y equal to x minus 1. Okay, because because in my opinion, the function g we can decompose by 2x minus 1, que es the slang, minus 5, que es the remainder, minus 5, que es the remainder, divided by divisor, que es x minus 2. And the apport for this part is the slang asymptote. And the apport for that part is the vertical, at least the bottom part is the vertical. In this example, we have, let me use it again, another rectangular coordinate system. I forgot to do in decimals, and you don't remind me, guys. It's okay. Don't worry. Let's do it. We have time. Okay. At least no completing the graphic. Not important for me now. Important for me now is do the graph of this line. And you see that y equal to x plus minus 1, y in excess negative 1. Let me make it zoom to see clear. Negative 1, I plot that point. And from this point, the slope is 2 positive, 2 over and 1. And you obtain the second point, and we connecting both points by the line. And this is my famous slant asymptote. Yes. Something like that. Oh. Sorry. I am doing no well. This is slant. But in my problem also, we have vertical and 2. 2 is easy. 90 degrees. 90 degrees and 2. Another vertical. Back color dotted line. Passing to. And the graphic, we are doing this much. And you apply more sophisticated technique we are doing next class. You apply similar to this. Oh no, never touch. Illegal. Approach it and approach. And the question that maybe fly in the air is, and the curve could be possible cross it or touch the slant, yes. Suppose you see one example. The thing is totally illegal is the vertical, never. But the slant and horizontal, yes. It's not frequently happen, but could be happening. Seldom. Okay? I don't know if it's good. I think we have. Yeah, it's both. Let's do it both. Let's see this example in the small slant, and you see how you can do that in easy way, guys. Okay, remember, we are living in the United States of America, 21st century. We have technology, we have internet. Okay, therefore, doing graphic by hand is sticky idea. No good. Now, let me try. Boom, boom, and boom. This is the graph you see before. Do you see this one, right? No, no. No?
Yes.
Okay, look at this is the graph of the first example. Okay, look at my organization. I copy. You can write, if you want here, not exactly the name in function notation, you can write y. It's good. And this is, we have here the vertical at x equal 1. Look at that. We flash it to see. And the slang at y equal x plus 1. You see how the curve in blue color approach it, pero never touch. Another example maybe is example 5. Let me see. No, this is another example. Okay. Let me come back again to the whiteboard and I write something and that's it. Erase the board. Let me share the screen. Board. You see my whiteboard completely clear?
Yes.
Okay. Okay, so now this is, I want to explain in detail now. The guideline that we are using universal, my students, to do the graph of the rational function is 7 steps. I want if you are doing no crazies, in this order. Okay, this is the guideline. No. To do graph of rational. Okay. Step number 1, super important. It's the first. Is I copy for the book. Say this: they are polynomial with no common factor. They are polynomial with no common factor. I don't understand very well this progress. Well, the thing is clear. You take the function f of x equal q of x divided by q of x, and you factorization. Suppose the factorization is the first thing you should do is factorization. Factor 4. Suppose we have x minus 2, x plus 3, and x minus 5. And the top. The bottom we have x minus 2, x minus 5, x plus 4. And you see clear like water, the factor gets cancelled. And this factor gets cancelled as a whole. And the factor can stay alive in the denominator we're using to find the vertical axis. Okay? And maybe you see the question will fly in the air. It's one of the professor and the factor can stay in the top. What's the meaning of that? Let's see now. You understand the step number 1? Guy, don't do anything. Factorization. And then in the 99% of the problem, we have no hole. The hole is weird. You see it cancel out. Of course, intentionally, I put some problem with the hole. No? Okay, so now number 2 is classical find y-intercept. Because this is a super important point in any graph. It's a graph that the curve crosses the y-axis. And the formula to find this is evaluation. Are you familiar with this formula, right? Number 3 is find the x-intercept. Here the formula is you take the f of x and you enforce it to be 0 and you solve that equation. because it's equation, maybe linear equation or quadratic equation, depending on the example. For example, in this example, I highlight in green color the factor that stay alive in the top is x plus 3 equals 0. Therefore, x is equal to minus 3. And the famous x in a set at the point minus 3 0. Okay. It's important to say something more. I write here in general way. However, in the particular rational function, you know very well f of x is p of x divided by q of x. So you enforce it to be 0 that, guys. It's obvious that q no participate in the game because the responsibility to be 0 is only for the p. Now to say this idea that f of x is 0 is equivalent 100% to see p of x equal to 0. In other words, shortcut, super easy. You take the polynomial in the top, the factor to stay alive, you enforce it to be 0, and you obtain the x in a set. Super important points. X and y. Clear?
Yes.
What is the fourth step? The fourth step is very fast. Always. Oh, this is easy. Because you take the Q part, the Q part that you ignore here is useful now. You take f of x is equal to p of x divided by q. And that part, I don't care, p. P is not important for me now. You take q, and you enforce the q to be 0. Of course, the q can stay alive. In this case, is x plus 4. Equals 0, x equal negative 4. And I know very, very well. At negative 4, we have very capacity. And this, in my opinion, is my way to do this. This is the crucial moment in which you are doing one roughly sketch by hand. Maybe it's useful for the last moment in which you copy in one dimension, not in two dimensions, or real number. Very cool. Or real number from positive infinity, negative infinity, 0 in the middle, and you plot negative 4, gets a vertical asymptote, negative 1, negative 2, negative 4, plot something like that. This is important because you split the all real number in two parts, and negative 3 gets here. So you using vertical asymptote and the x in a set to make here negative 3 comma 0, no, negative 3 comma 0 is the point in two dimensions, to make a partition of the potential point. When you complete the job, you select. So for example, this is not happy answer. However, I select one arbitrary. So basically, let me explain more clear. Okay. You using the asymptote and the x in a set, you split all real number in one interval, two interval, and three interval. Entonces, the classical question, bueno, professor, how many points you obtain to plug it in the original to complete the graph? Well, that depends on the problem, but you take at least one here, bam, maybe negative 5 or negative 6 or negative 7. You take one here in the middle, and between -4 and -3, maybe -3.5 or 3.6 or whatever. And you take in the other interval que maybe a 0, maybe 1, maybe 2, maybe 3. Okay, entonces now at least 1 point in each interval give me some idea. So you want to see more clear, you increasing the number. But that's super easy doing in decimals. Okay, let me finish the explanation. Well, number 5, remember it's 7 points, is determine the horizontal asymptote or slant. And remember, they are mutually exclusive. Oh, in my problem we have horizontal or no, and we have slant or no, but both no, never, right? And the thing that we are doing is the analysis, degree analysis. Degree analysis is the key idea to determine if we have no horizontal. You have to remember, guys, the rule. Okay, right at the beginning, the student don't remember very well, but I see. Number 6. Number 6 is, we almost finished, guys. Is analyze, so I want to call test of symmetry. Frequently, the student forgot. Very important. I want to explain why. Test of symmetry. Test of symmetry is remember the determine si function is even, si es odd, or neither. To determine this, you make a reflection. See, when you make the reflection, the function stays the same, doesn't change, it's even. You make it a reflection. The reflection is equivalent to reflect not in the y, sino in the x-axis. It's odd. When you make a reflection, nothing happened. Nothing happened, no. It's not symmetric. So it's completely different expression. No. Es obvio que es neither. So what is useful? The useful application is, look, suppose that the function is even. If the function is even, you don't need to analyze positive part and negative part. No. Why no? Because you have here in the positive part, suppose I pick 1.2 and you obtain 4, because in negative 2, you obtain also 4, because it's the same value. So basically, the idea is that you don't need to repeat this stupid computation in the negative part and the positive part. No, because the function, I know, is symmetric with respect to the y-axis. This is classical even. What about odd? Well, odd is symmetry, but another kind. Suppose que es something like that. Suppose que the function is like that, but the function is like that. So suppose que you pick, you don't do numerical, you are doing algebraically. You pick one value 2. And you obtain 4. Nice. And you pick negative 2, is the image, and negative 4. So now you don't need to repeat the negative part. You are doing the positive part, the person I like, and the negative part is the opposite. This is odd. Symmetry will respect the origin. No symmetry, unfortunately, we need to do the negative part and the positive part. Unfortunately. Double work. So you spend 1 second or 2 seconds to analyze the symmetry. And you, I want to emphasize this and that. And finally, guys, 7. I want to explain super quickly because the time is over. Is plot additional point. Additional. And this point is crazy. No. We programming this idea here and this step 4. You are doing the planning of the partition of the x-axis. you determine the minimum value of the additional point you put. Okay, don't worry too much. Next time, next week, of course, I will bring 4 strong examples that we, analyze in super detail everything about the rational function. Okay? Remember, we are the best in Miami-Dade College. Okay? Any problem with the grade, you can see in Canva. Any problem, I can explain your grade. Okay? Bye-bye, guys. See you.
Bye, Professor.
Soon I will send the video, the link of the video. Bye.